inviting me today. Okay. Yeah. Yes, today I'm going to talk about the Himalayan belt and specifically about one of the major tectonic structures there, and which is the South Tibetan Detachment System. So, not changing slide. Okay. Yes. So I will just start with a very brief introduction on the belt before going toward what was the actual study. So for those who are not practiced with the Himalayan belt, this is a orogenic belt derived from the collision between the India and the Eurasia plate between 59-61 million years, which is a diachronic and oblique collision where the Indian plate is acting as a lower plate, whereas the Eurasian plate is acting as upper plate. So this is kind of similar to what has been, for example, reconstructed also for the Trans-Hudson origin in Canada here for the Canadian Shield, where we have Superior colliding with the Churchill province. And actually, this is kind of typical to use the Himalayan belt as a collisional origin, as an example of collisional origin, because of several reasons. First of all, it have a kind of a lateral continuity of the main structures and units along the belt. So you can see here different colors there are for the main tectonic units and the major tectonic boundaries. And also what we can see here in general in Himalaya is that there are several north-south trending valleys that cross-cut basically the main tectonic units and structures. And these are very deep valleys, offering basically natural cross-section of the belt. So we have spectacular exposure. And also the Himalaya is still affected by an ongoing deformation. So it's also used for neotectonics study. So all these features make the Himalayan belt like a classical laboratory. And specifically today, I'm going to talk about the South Tibetan Detachment System, which is here basically the uppermost unit, the uppermost structure. This is a syncollisional detachment. So it means that it was active during the main exhumation of the belt, which occurred during the Oligomyocene. And basically, this is a structure between two main units, which are in purple, the Greater Himalayan sequence, which is considered the highest metamorphic complex of the belt, reaching around the amphibolite phases with lots of melt and migmatite. And this is at the footwall of the structure, whereas at the hanging wall, we have the Tibetan Himalayan sequence rocks. There are metasedimentary rocks formed up to the upper green sheet spaces, but mainly from very low grade to metamorphosed, sorry. And these structures has a top down to the north sense of shear, which is kind of in contrast with the sense of shear recorded by the major thrusts along the belt, which are south-directed thrusts. So these structures have been widely used in literature to reconstruct the tectonic models that later on have been also applied elsewhere around the world. And actually, it has also a complex architecture, because basically this is a system where we have a major mylonitic zone affecting, as I was saying before, the high-grade rocks of the Greater Himalayan sequence and the metasedimentary rocks of the Tibetan Himalayan sequence. But at higher structural levels, there is another feature that, for example, in the Everest area here is represented as the Chomolungma detachment, which has the same kinematic and sense of shear, but basically it is in the brittle regime. So we have like this complex architecture with those two structures, where the major of the deformation has been clearly accommodated by the mylonitic zone. And there are lots of studies, especially in the Everest area, using quartz within the quartz-bearing lithotypes involved by the mylonitic zone, using quartz just to reconstruct how the shear zone was evolving through time, in sense of how was the shortening, how much was the compression and the telescoping of the isotherm and in terms of how much was the stay rate. And we also have age analysis and dating on the lower structure and the upper structure. So here there is just shown a summary picture from a review of Waters et al. 2019, where basically it shows actually how we have the coupling of the Greater Himalayan sequence, GHS here, and of the Tibetan Himalayan sequence, DSS, in this picture, where we have basically this high strain zone passing from the amphibolite faces toward lower grade rocks at the hanging wall, so from 650 to 450 Celsius degrees in the mylonitic zone. And after that, younger, like less than 15 million years old, we have the localization of the upper brittle faults, which in the Everest case is just within limestones at higher structural levels. So it has been reconstructed basically a temporal evolution of this structure, but the story is far from being like complete. Like there are several doubts still on these structures and questions, and specifically the one on which I focus the most is that this complex architecture is actually not really developed all along the belt. And this means that there are several areas along the strike where we only have the lower detachment, the mylonitic zone, but not the upper brittle fault, or is not really clear, like not all the authors agree that there is really this detachment cropping out. And so my main question in this case was, can we explain or can we try to identify reason why we can have or not the development of the brittle structures? Like if we think about the picture of Folsen and Cavalcante 2017, he basically summarized how a shear zone changed from lower structural levels, from the lower crust or middle crust toward higher structural levels, basically from a thick and wide mylonitic zone that becomes narrow and narrow going toward the upper crust, where basically the deformation mechanism within the shear zone changes in function of the lithospheric stance profile. Here we have, for example, plotted for quartz in light blue on the left and for feldspar in purple. So basically we have a changing in the major regime recorded by the minerals while they are accommodating the deformation within the shear zone. So my question was, can we analyze this trend in the areas where maybe it's more cryptic to find the upper brittle fault, or in general, this discrete brittle fault? And so I particularly focused on 3 areas, which are all in central Himalaya, and there are in Midwestern Nepal, which are the lower Dolpon, the Kaligandaki Valley, and 2 more valleys in the Manaslu Range. And basically these areas, despite they have been widely characterized from a structural point of view in the sense of how many deformation stages were recorded by rocks and the folding styles, there are very little investigation about how the affected rocks are deformed, like the same kind of approach that indeed was used for the Everest area. So in this case, actually, the lithology change, and is not anymore quartz-bearing lithotypes, which is maybe the most studied in the Himalaya, but in this case, these are marbles, and are marbles and pure marbles. So actually, there is one more difficulty studying these rocks, because actually, it's even hard to detect where the shear zone boundaries are in these areas. Because since these are marbles and pure marbles, means that they have more than the 75% of the bulk mineral volume just made out of calcite, and therefore with minor second phase minerals like stronger clasts that can develop asymmetric structures, or like micas that can develop SC fabrics. So basically you can walk for hundreds of meters along the valleys without finding any kind of kinematic indicators that you can use to constrain the shear zone boundaries itself. And even if we go toward a smaller scale, like if we collect all the samples we can and we look at them under thin section, can still be quite hard to detect kinematic indicators for marbles because calcite tends to re-equilibrate at even low temperature very easily. So it tends to lose the shape. So for example, we can have oblique foliations in quartz-bearing rocks or dolomite, which are less preserved in carbonate. So we need to use a different approach to get the same kind of results obtained for the Everest area in this case. And therefore, to get the, for example, stress orientation and kinematics, what is the strength of the deformation recorded, or what was the strain rate? So what were the also the differential stress recorded and the deformation temperature or the shortening and the simple shear contribution. But in this case, what can help us is studying how the rocks and how the minerals internally reorient themselves while they are deforming. So basically, the assumption is that, especially in the case of limestones, where we have originally grains of carbonate that are fine-grained and completely unoriented, while the shear zone is working, basically we have that grains tend to recrystallize and reorient themselves to make the deformation going easier, like not to have to compensate strain hardening and keep the deformation going plastically. And in the case of carbonates, we have typically grain boundary mobility mechanisms like grain boundary migration or other dynamic recrystallization mechanism. And we also have twinnings, and particularly there is one kind of twins that develop in calcite for deformation, which is called like E-twins. So we can basically go and to a smaller scale, the crystal lattice scale, to see what was the reorientation of the grains overall. And the more they are oriented, the more it means that the rocks are strongly deformed. So we have also a sense of the strength of the deformation. And we can plot basically the orientation of the grains in what are called pulp figure here on the right. So basically stereographic projection of, for example, in this case, the z-axis, so the elongation axis of calcite. So I will just go back to one of the study areas. I'm just showing here the Kaligandaki Valley because maybe it's the most famous of the world. It's one of the deepest gorge of the world. But this is just to say that also the other areas really share similar properties. Like in this case, we have marbles, like in the picture here on the top right. And the ductile shear zone is affecting the greater Himalayan sequence rocks and the Tibetan Himalayan sequence rocks. So the high-grade rocks and the lower metamorphic grade rocks. And with what was already described as a high strain zone. So where the foliation is really with a constant orientation within the affected volume. And if you look again at all the information we can get from the meso and micro scale, we can see basically from the few kinematic indicators that, yes, we are in the South Tibetan Detachment System zone with the top down to the north sense of movement and kinematic indicators. And at the micro scale, we can also see where the samples are more heterogeneous in the sense of the mineral assemblage, that there is a little bit more preserved also the oblique foliation, for example, in carbonate, not nicely as they could be in quartz for obvious reasons, but still preserved. And also we can see that carbonates tend to have a shape-preferred orientation consistent with the foliation itself or at low angle making the oblique foliation. So that we can just already say something. That is that carbonates are deforming kinematically with the foliation itself, where the foliation in this case is marked by mineral, like in the footwall, they are diopside or anyway high temperature minerals, wollastonite, pyroxene. Whereas going towards the hanging wall, we have the biotite zone and then the biotite white micas or just white micas. So we have the same temperature profile that was described for the Everest area between 650, 400 Celsius degrees if we just look at the mineral assemblage. Then we can go toward the smaller scales to try to get the other information. In this case, I just showed you some of the fault figure listed in row for some of the main information from the involved unit. And basically what we can see in the column are the different crystallographic elements and plane I plot using a X-ray texturgoniometer as an acquisition method for the crystallographic preferred orientation. So I won't go in detail on what all these fault figures mean separately, but what I would like to say is that the main information we can get from these plots are that the rocks are kind of intensely deformed, and that there are two major deformation mechanisms that we can see that are the grain boundary mobility that we have seen before and twinning. And what we can see is that, especially looking at the E-planes, we have E-twinning reoriented the grains synkinematically with the South Tibetan Detachment System sense of shearing. So to synkinematically with the top-down to the north sense of shear. And then just taking time on saying that because, well, usually people where they say we see twins and on calcite, they immediately think that carbonates were deforming at temperature below 250 Celsius degrees, more or less. And that's because actually twins tends to dominate as deformation mechanism below 400 Celsius degrees in general. But if we look, for example, at the picture here, the graph of the Bresser and Spires 1997, where there are plot the different deformation mechanism like E-twins in green, or some of the major grain boundary mobility related mechanism for in red and light blue. Well, we have an overlap of these two mechanisms, but actually at temperature below 400, 300 Celsius degrees. But what we have seen from the microstructure is that carbonate here recrystallized synchronously with the synkinematic foliation, so that we expect that calcite was deforming at higher deformation temperature, like at least 450, 650 Celsius degrees. So we are not in the range where twins can dominate and reorient the crystal lattice in function of a non-coaxial flow. So here my question was, can we check if they were like recorded through time so that we have like an overlap of the two deformation mechanisms, or if they are recording two different pulses of the deformation or completely different regime? So to try to understand this, what I've done was to try to use the paleopiezometers and the paleotemperatures that we have for twins and for dynamic recrystallization in carbonate. So I will just start with twinning. We can basically use the twins width and density to reconstruct the possible temperature, which in this case clearly is below 250 Celsius degrees. So completely different and lower temperature than what was recorded by the mylonite foliation index mineral. Whereas if we look at their density within the grains, still in this case, I just use a universal stage to check whether they were E-twins or other twins that were unrelated to the deformation. So if we just check the E-twins, we can understand the differential stress and the strain rates recorded, which are, in the case of twins, for the differential stress recorded by the calcite grains in monomineralic assemblages, were around 100 to 200 megapascal, which is kind of a still normal range of differential stress values that we can find in detachment zone, and with still natural strain rate of 10 minus 14, 10 minus 12. I will go back to that number later. So now we can look at the dynamic recrystallization, which were the grain boundary mobility mechanism. So we can use the grain size distribution of at least 1,000 interconnected grains with less than 1 or 2% of second phase minerals in between the grains to reconstruct the differential stress and the strain rates recorded by the mineral phase during the deformation. And for the same rocks, basically, in this case, the differential stress was around 5 to 15 megapascals. So one order of magnitude lower than what we have seen before for twinning. Whereas the strain rate is almost the same general natural strain rates. So for the different temperatures recorded, we have from 10 minus 11, 10 minus 12, second minus 1. So it looks to me that the two deformation mechanisms are not recorded just for different deformation temperature, but also for different differential stress and different strain rate. Not that much strain rate, but different differential stress. So the question was, since they both record the top down to the north sense of movement of the South Tibetan Detachment System, what is the kinematic vorticity recorded like? Are there any changes in the flow, in the non-coaxial flow? So to do that, I used the oblique foliation for carbonate and where they were best preserved, and the how much the crystal lattice was reoriented by E-twins for checking the mean kinematic vorticity recorded by twinning. So in the graph on the lower right, they are just shown for the different areas. In the circle, we have the areas for the lower Dolpo and the Manaslu valleys. And basically what we can see for those two valleys is that we have the grain boundary mobility mechanism developed with the oblique foliation occurred in a simple shear dominated flow, whereas twinning occurred for a general shear flow, but with strong pure shear contribution. If we look at the Kaligandaki Valley's results, which I, for simplicity, plotted in the graph above, we have the similar trend, like in purple, we have, in triangle in purple, we have the twinning, and in the squares, we have the grain boundary mobility. So we have a similar trend, but with a major overlap. So slightly different, but kind of similar. So trying to combine all this data together, what we are seeing now is that basically the two deformation mechanisms that were occurring basically within an error bar, the same strain rate, so a same event, we're basically recording differential stress and temperature. And if we use the lithospheric strength profile, like it is usually done for quartz and feldspar, we can see that it means that we have two different stages recorded by the microstructures. An early stage at lower structural levels and therefore higher temperature in the plastic regime, therefore with lower differential stress. And we have transition toward a brittle plastic deformation recorded by twinning, still when the rocks were under generally plastically deformation with a top down to the north sense of shear. And generally speaking, with a decelerating same path, that means that we have a lowering in the kinematic vorticity value. So it means that also if we are just looking at the ductile mylonitic zone, we can see a kind of a temporal variation like it was seen for the Everest area where we had the localization of the upper brittle fault. So I would just like now to compare the results from the Everest areas or other areas where it was analyzed for quartz with the results I got for this 4 valleys in these 3 areas. So I'm just using the data summarized by Watersat 2019 and combine it with the D2 early stage and D2 late stage for the Midwestern Nepal. So we can just start comparing the deformation temperature. And basically within the mylonitic zone, we have for that the deformation temperature are quite comparable for the quartz-bearing rocks and the early stage of shearing of carbonates from what we can see from the mylonitic foliation and the index minerals. But that's completely different than what we can see for the twins, which are rather more similar to what have been supposed for the upper structural elements, so for the upper brittle fault. We can compare the differential stress. Our differential stress for the D2 early analyzed from carbonate are really similar to what was analyzed and obtained for quartz in the lower mylonitic zone. And they are 1 order of magnitude lower than what was estimated by twinning. Then we have the strain rate almost fall in the same range of natural strain rate. And the kinematic vorticity with some overlaps are more similar for the one from the quartz-bearing rocks are more similar to what we have for the D2 early. So before the decelerating same path. So these are basically the combination of the literature and what was shown previously in this presentation. So now I would like to show that basically what has been seen in the quartz-bearing rocks is that we had a localization of the deformation toward upper structural levels, or anyway, we had a new localization of the detachment itself. If we think now about what we had in the mylonites, we had basically rocks that were able to keep deforming under a plastic condition even when the temperatures were way below the temperature at which quartz can deform plastically. This means that if we plot now the lithospheric strength profile for carbonates, well, the brittle plastic transition is even below 170 Celsius degrees, or some authors argue lower than 100 Celsius degrees. So until this temperature, the deformation can keep going overall plastically with lots and lots of twins in all the grades. So the main conclusion from this, or at least a possible first solution for this, is that in these areas I've studied, where the upper detachment is at least cryptic, and not all the authors agree that there is actually a really new localization of the structure. Well, the possibility is that in this case, the mylonitic zone was still working at lower deformation temperature, and there was not a strain hardening. So basically, the deformation was able to keep going without any necessity to a new localization of the deformation until basically the rocks reach the brittle deformation regime. So we can also have their brittle features. And basically this was the work and the main result, and particularly showing that the variation of the lithologies along the strikes is probably kind of important when we need to define tectonic models, when we are defining the tectonic model, since the structures seems to be laterally continuous, but actually they have variation in depth and in the overall architecture. And that's all. These are the main people with whom I did the work with. Thank you.